Thank you so much for the kind introduction. First of all, I really have to repeat the words that all the previous speakers told us. I'm so much excited that we all can be here in Berlin at this exciting event, talk to each other, and also having presentations and watching these presentations. That's so great, and I really like that. Okay, let's talk a bit about sensor fusion. If you want to develop an automated driving system or an ADAS, then you typically find such a block diagram, which is a simplified, of course, a very much simplified version of the technical system behind that. On the right-hand side, you find the actual vehicle control. That's the action that have to be performed in order to control the vehicle, that's steering, braking, and so on. And on the left-hand side, you find the actual sensors that drive that whole process. In between, we typically have two major building blocks. On the right side, the driving function that gives the control commands to the vehicle, and in the left part, we have the so-called sensor fusion or environmental modeling part, where all the data of all the sensors go in, and we get out a unified representation of the vehicle's environment. This process is then typically called sensor fusion. But I do not want to talk about sensor fusion that much in this talk. Actually, I want to talk about the development of such a sensor fusion system. And I would like to try to find at least some parts of the magic that go on when we develop or when such sensor fusion systems are developed. So let's have a look at a very typical development approach that we have seen many times in the world and also at our customers. So typically it all starts with some architectural design where some clever people make up their mind, okay, how the architecture of such a sensor fusion system should look like. From that design, an implementation phase can start, which takes the architectural decisions and all the components and converts them into some source code. If we have that source code, then typically there is some tuning phase and parameterization phase where lots of engineers and developers parameterize the system, find parameters and tune them so that the system does what it should do. Once we have those parameters, we can now run the system and validate it against some reference data. We can calculate some KPIs and then see whether the system fulfills the requirement or not. Typically, when we do this, the validation the first time, then it often fails. Now the developer may ask the question, okay, how can I fix that? How can I do that the validation passes? And the very first typical step then is to adjust the parameters of the system, because that's typically the easiest step. For that, the developer does not have to change any implementation, just changing some parameters, and then the system will behave differently. How does this look like? How does it could look like in practice? Very often, there is a developer that replays scenes of recorded data, and then tries to find parameters that make the sensor fusion system work better. This has lots of disadvantages. First of all, the parameters that the developer then found or set, they are difficult to trace, right? So once the parameters are set, it's not that easy to later on to find out, okay, what's the origin of those parameters? Which effects causes those parameters? Then, if you do it like that, then we typically do not have any separation between the, let's say, sensor parameters or parameters that are responsible for modeling the sensor and parameters that are rather responsible for, let's say, kind of tuning the algorithms. And finally, while doing so, of course, you highly depend on the actual tuning expert And of course, this introduces high manual efforts. After this process, the validation of parameterization, the validation restarts, and let's assume that it still fails because this was not enough, so changing the parameters is not enough. And the next step that the developer could go and could take is changing the implementation that he has at hand. And let's have a look how this typically or very often look like. When we look at the source code of sensor fusion algorithms, then of course we find those typical algorithms in there, Kalman filters, association methods, and all these things that we all know since decades. However, if you have a closer look at the source code, then you very often find a lot of conditional expressions, so we find many of those if statements. And what follows on the if is some condition, and if the condition is met, then the developer typically does some assumptions about the underlying system or the sensor, and he writes that down in code. Let's have a look at an example. Let's assume the system can distinguish different object types, and the developer found out that there is some issue with the object type vehicle. Then he writes down if there is a vehicle. Then additionally he finds out, okay, it's something related to the crossing action that the vehicle performs, so he writes down, okay, and if the vehicle is crossing. There might be some other conditions, like the vehicle is viewed from a certain angle, so that's the angle how the sensor observes the vehicle. But there might be also conditions that are based on the environment, like the lighting or any rain or humidity condition. If the conditions are then met, then the developer may decide to set some assumption about the underlying sensor. Here in this example, he finds out, well, under these conditions or under those conditions, the sensor gives me a range measurement with a high range error, and he writes this down in the code, and then it's there. And I have another example for pedestrian. The developer does the same thing or similar thing. He finds out all these conditions, and then he sets the range error of that sensor to another value, let's say to medium error value. Let's generalize those conditions a bit. So typically, if you look at those conditions, then they contain physical quantities. It's like the object type, the object position, the object driving direction. Or it's environmental conditions, like the lighting. And of course, we see any combination of these conditions. What is then done, or the action then that is performed, if the conditions are met, then there is some modeling taking place. Typically, we have sensor modeling or system modeling that is done by the developer. And finally, we also see lots of workarounds that are still needed for many of the algorithms that we are currently using. Those workarounds, they come from architectural limitations, algorithm limitations, but also, of course, from compute limitations. So what's wrong with those conditional statements, with all these ifs? Actually, nothing is wrong with these ifs as long as we can justify and trace them. So that's the important aspect here. We need a way, or to find a way, to justify those conditions so that, for instance, another developer, or after 3 years, someone understands why this if is in the code, and is this if still relevant for, let's say, my new sensor setup, so that I can reuse that code for the next project. So justification and traceability is really a hard requirement. And if you look at typical requirements for developing safe software, then you always find this traceability requirement. And for normal code, you typically have a requirement that you can trace against. There is a requirement, and then you can link this requirement to that piece of code, and the work is done. Then this is justified. However, as those conditions typically contain physical quantities and typically describe the real world, you typically do not find that much hard requirements in a specification document. The same applies for the modeling. Also, the models that we then find, they need to be justifiable and traceable as well for the same reasons. And as a no-brainer, the workarounds and limitations need to be reduced. Let's have a look at those conditional statements from an architecture point of view. So don't be afraid, I won't go through the equations now. But this is a simplified example of a nowadays architecture for a typical sensor fusion system that we find in many ADAS at the moment. And if you do this architecture well, then you have lots of points where models can be entered and where models are used, models for the sensors, for the system, and so on. And those if statements, those conditions, they are now added at exactly these positions, and there's one if here, one if there, and soon you will have many of those if statements everywhere in the code, and each of them need to be justifiable and traceable in order to reuse them, but also to be safe in the usage of that algorithm. If you look at the typical sensor fusion system, then you find hundreds of those statements, and many of our customers, they complain that it is really, really hard to maintain those conditions, those ifs. It's so hard for them to control them and to make any reuse also of the code. And from our perspective and from my perspective, this is one of the magic parts. So finding and applying those conditions, this is a very important part of the magic in sensor fusion development today. I've shown to you an example for vehicles and also for pedestrians. But we all know there are much more objects that current ADAS need to detect and need to handle. So we have animals, we have bicycles, motorcycles, we have bicycles, and we have trucks, and so many more objects that we need to handle now and in the future. Currently, it's 5 to 10 different object types, and you can already see this in the slides. This makes this whole process and the whole problem even worse. For that reason, we propose a different approach how we all should develop sensor fusion systems, and we call this a data-driven development approach. The major change here is that the whole process does not start with the architecture directly, but it starts with a characterization phase where the system and the sensors are characterized. Let's have a look how this may look like. So let's have a look at this typical scene here where we have multiple sensors, and for now let's reduce that to just one sensor, and let's even more reduce that to a single quantity that sensor observes. Let's say this is the range measurement that this sensor gives to us, and we want to model this range measurement in our system, and we want to find a model for that. So the developer, for that reason, wants to see some histogram over the range error of the sensor. For that, he is using ground truth, converts the ground truth to some range, expected range measurement, and then simply subtract it from the range measurement of the sensor. And from that, he can then extract such a simple 1D histogram that shows the frequency of the errors over range error, over the range error, sorry for that. And in this example, we see that there are, let's say, some moderate errors on the left side, but there are also some really high errors on the right side here in this histogram. And the developer may ask the question, why comes this? Why is this? Why we have those large range errors on the right side? And the developer has an assumption about this. He says, well, it might be caused by different object types. So let's test that and let's try that. Let's take those objects and the object types as a condition for the range error, And he has another assumption in this example. He says, well, this range error might be influenced by the viewing angle. So again, that's the angle how an object is seen by a sensor. So 0 degree means the sensor is from the rear, the object is seen from the rear side. 180 degree means the object is seen from the front side, and 90 degree completely from the side. Now, the developer selects the high range errors in this histogram. As soon as he does this, then the system can calculate some other values for the conditions. And now you can see that his assumptions were right, that those large errors, they mainly come from vehicles for this sensor. So which means that the sensor seems to be pretty good in measuring the distance of the pedestrian, but it's not that good in measuring the distance of the car. And that's what we can see from the diagram. Also, the second assumption, he was right, that the aspect angle, so the viewing angle, influences the range error. You can see this in this heat map on the lower right side. Now the developer selects the cars only, and if he does this, then the effect gets even stronger, and now he's sure that he has found a model, the conditions, and the model for his system. He selects, let's say, now the center bar, the 90 degrees value, which is the worst one, and then he sees that the range error really goes down, and he really isolated the high range error for those two conditions, and from that he can build a model with the conditions and the actual model. And this is how he can trace that. So for finding out that model, there was no sensor fusion at all involved. It was not executed at all. He just looked at the sensor and the reference data. There was no code involved, no coding. So you can just do this using those diagrams and write this down, and someone else can then prove that. And if the sensor changes, then those assumptions can be reproven again with a new set of data. They can check against whether they still hold and whether the sensor model still looks like that. So we have found the model, and we have justified it, and it can be traced down to those diagrams. And of course, we need to do this for all the sensors. But the good news is we can do this per sensor individually with some kind of scales for the developer. Once we have found those models, and of course we have lots of those models, we can now go back to the architecture. And if the architecture now contains something like a plus button, then we can simply add all those models to the architecture. For that, the architecture itself doesn't change. We just add some more models, so we can reuse the existing architecture and add all the models that we have found in a very quick way. Once we have done this, then the implementation can be automated because the architecture itself is fixed. We just have add models for that. This is the previous version that I've shown to you. So this is how the code looks like if the developer writes this manually. And it would be very similar if we auto-generate that code. The major difference is now that we can trace that, and that at all these conditions, we have a traceable link to the tool or to the data set that produced those conditions and the model. Let me conclude my talk and summarize what do we actually need in order to have such a workflow. First thing is we need a scalable sensor fusion architecture that contains this plus button that I've just shown to you. And with that plus button, we can add all the models that we need to model the sensors and the systems. Of course, we need tools which do the things that I've shown to you. We need tools for sensor and system characterization so that we can justify and trace the conditions and the models via data. That's the important aspect here. By that, we put all the knowledge that we have about the sensors and the system and the environment, we put all the knowledge in the models and not in the code. Of course, the code comes out of those models and of the architecture, but the actual knowledge is contained in the models and somewhere outside of the code. We need tools for validation, that's obvious, I would say, for calculating the KPIs that we need for that. And for the overall process, we need reference data at object level. And of course, so many more things that I can't mention in this talk. So the good news is that we can do this whole workflow with today's available algorithms. When I say today's available algorithms, then I mean all of those, let's say, classical algorithms that we can see in the market at the moment, especially for ADAS, so things like Kalman filters and so on. We can do this, however, only with some, let's say, limited modeling capabilities. They come from the algorithm limitations. And we can do this with limited modeling capabilities for urban scenarios and high-resolution sensors only. And I have a final example before I finish my talk. What we can see here is, let's say, a typical sensor model for an ADAS that we have in the market. Let's say it's simple ACC or AEB working on a highway. For those systems, we typically model, let's say, a radar sensor like this. So we assume that all the radar measurements, they come from the rear side of the vehicle, and then we have such a, let's say, Gaussian distribution in the center of the rear side, and we can model it like that, and that's fine. What we see for urban scenarios and high-resolution sensors, that's things like that. That as soon as we rotate the vehicle in front of the sensor, and that's all the time happening in urban scenarios, then the sensor models must be much more complex. And we cannot derive those sensor models, let's say, by manual tuning and manually finding the conditions and the models. For that, we need a data-driven workflow as well, independent from the fact that also those algorithms still have to be developed, at least for production. So thank you for listening to my talk, and now I'm open to answer all of your questions.
Okay, great. Thank you. Let's see whether there are questions. Okay, questions for Eric? Going once, going twice. There you go.
Hello, this is Thomas from AVL. Thank you for the interesting talk. A question to the data-driven approach is, you don't have a chicken egg problem because you have to generate a sensor setup, you collect data, you do ground truth data, and then you go into the optimization? This is the first question. Second question is, a lot of parameters, is this done manually as you have shown it in your example, or do you use some kind of optimization software and frameworks? Thank you.
Yeah, I start with the second question because that's the one that I completely understood. So for the development of, let's say, rather classical ADAS, we believe that such kind of, let's say, manual tuning and let's say, aided parameterization is really sufficient, or not sufficient, but is really a benefit against several things that we have seen out there at the moment. So it's not, let's say, automated. It's kind of aided, so that you can, let's say, quickly go through your data and find those conditions. But still, an expert has to do that with some expert knowledge behind that. Coming to your first question, I missed the term before the word problem. So that's why I cannot answer. Actually, I believe that we can kind of avoid the chicken and egg problem, because we can characterize the sensors and the system independently from the actual sensor fusion system, because that's physics, kind of. What we want to find out is the underlying physical behavior of the sensors and the objects that we want to have, and those physical parameters and the physical behavior, this is there with or without sensor fusion. And what we propose is that you should find out those physics without the sensor fusion for not running into that chicken egg problem, actually.
Any more questions? Okay, if not, let's give another round of applause to Eric. Fantastic.